we left off talking about mixtures, the differences between mixtures and compounds. And so the two types of mixtures we were talking about were homogeneous and heterogeneous. We pretty much know homo meaning same and hetero meaning different, that a homogeneous mixture would be something that looks the same all the way through. And the example here is like you've got Gatorade on the right and you've got an oil and water on the left. Now Gatorade, you'd look at it and it looks the same all the way through. We would say it's a homogeneous mixture because the composition, as it said here, is uniform all the way through. You look at the top, it's the same color. You don't see any bubbles in it. You don't see any precipitate in it. So that would be a homogeneous mixture. Everything is in solution. And we'll learn more about what in solution actually means a little bit later when we talk about solutions. But oil and vinegar, if you shake it up really, really fast and then have a quick look at it, it may look homogeneous because the color is the same all the way through. But if you let it sit for any amount of time, as anyone has done, the oil starts to separate out. And those are parts of chemical interactions that we're also going to learn a lot about, pretty much in the last chapter we'll get to, is that the shapes of those molecules is really important in determining how they interact with each other. We're going to talk about polar and non-polar.
Excuse me.
Well, yeah, go ahead.
So for colloid, is that homogeneous or heterogeneous?
Colloid. That would be heterogeneous. I'm pretty sure. I guess it would depend on how uniform it was. I mean, a lot of colloids you see. I mean, there's there's certain areas where you have non-polar portions and polar portions.
Starch water.
Like what kind?
A starch water.
If it was that would be uniform. If it was uniform all the way through, but the oil and water mixture, it's not uniform all the way through. So even if something like a foam, for instance, would be homogeneous because that foam has the same chemical makeup any portion through it. So that would be homogeneous. Whereas oil and water would be heterogeneous. What am I looking at there?
This foam. What did you say? Foam? pH?
Foam, like a shaving foam or something like that. Sorry. No, foam.
I was just thinking about my cell phone.
No, your cell phone is not. That would be heterogeneous indeed. One side is glass and the other side is metal, so we could easily tell the difference.
So if there's a clear, distinguishable, I guess separated, it's heterogeneous.
Definitely.
Right? Okay.
Definitely. So, or if you have a solution of something, but there's precipitate on the bottom. Let's say you've got a saturated solution of salt. So the liquid part is homogeneous, but on the bottom you've got a solid. So you'd say that even though the mixture is homogeneous, you say that the container does not have a homogeneous solution in it because there's some precipitate
the salt
on the
is still
bottom.
Visible.
Yeah, exactly.
Okay, got it. Thank you very much.
So if you want to tell the difference between a mixture and a substance, you just sort of start with this decision tree. Where you say, does it have constant properties and composition, like all the way through? And if no, if the composition isn't constant all the way through, like for instance, a solution has solute, which is what we call the whatever's dissolved in the solvent. So water would be a solvent, sugar or salt would be a solute. That's not constant. There's different parts of the composition. So we'd say, no, it's not a pure substance. But if it's uniform all the way through, then you say, yes, then it's a homogeneous mixture. On the other hand, if you have something that's pure, that's a pure thing all the way through, it's not something mixed into something else. If there's just one type of substance in it, then yes, it's a pure substance. But if you react it in some way, can you separate it into different things? Now, an element cannot be separated into other elements chemically. You can do it by, like in a nuclear type reaction, by breaking down the nuclei. But we know by now, because I've been railing on it for so long, that chemical reactions involve electrons only. And so if you can break it down by either adding or subtracting electrons, then it's a compound. It's not an element, okay? So let's have a look at some of these things, give you an idea. So air, but when you're, like yesterday when it was really smoky, maybe not so much, but the air we usually breathe, would we say that's homogeneous or heterogeneous?
Homogeneous.
Yeah, homogeneous, because, you know, except for those times we can see it, then it's heterogeneous. But yeah, but normally that is a solution. It's a solution of gases, but it's still a solution. Anyone know what the solvent would be for the air we breathe? What would be considered the solvent of the air we breathe?
Is it hydrogen or nitrogen?
Which one?
The more abundant one.
Which is?
Nitrogen.
Nitrogen, that's right. Nitrogen's around 76, 77% of the air we breathe. So we'd say that the air we breathe is a solution of nitrogen. Now, gasoline. We consider gasoline a heterogeneous or homogeneous solution.
Homogeneous.
Yeah, that's homogeneous too. It's mostly octane, but there's a lot of other hydrocarbons in there as well. But if you just leave gasoline sitting, it doesn't separate. It's a homogeneous solution. Now this one's more tricky. What about milk?
Heterogeneous.
Hetero?
Homogeneous.
It depends, doesn't it? Depends whether it's fresh or whether it's been homogenized. Now, if you leave milk for a certain amount of time, it can separate. Now, when you buy like what's called homo milk at the supermarket, that means it's been homogenized, it's been processed, and something's been added to it, so that there's a lot of fat. I hate to say, because I love milk. There's a lot of fat in it that will separate if you leave it. And so if you add something to it, it allows the fat to stay dissolved in the solution. So I would say right out of the cow, it's heterogeneous, and then if it's been treated, it's homogeneous. It depends. Yes.
I think I don't remember correctly. I think once I saw on the label, I saw water on the milk
As one of the ingredients. Say water was one of the ingredients.
Yeah.
Yeah, because it's mostly water. Yes.
But if you drop a milk into a water, it would separate.
No, I mean, again, it depends on the kind of milk you have. If it's been treated, it won't immediately. It may after a long period if you dilute it enough, because it's mostly water, but it also has protein and carbohydrates and fat in it. And if you heat milk, we've all seen what happens when you heat milk. It'll curdle, right? Or if you add acid to it, if you add vinegar to milk, you precipitate the proteins, and they'll like sort of clump together and fall to the bottom. There's like a delicious Indian dessert that's made that way. But so that just shows it's a mixture. It doesn't show that it's heterogeneous. It shows that it's a mixture, that if you add something, you can cause it to separate. Now, what about the Twinkie here? We consider that heterogeneous or homogeneous?
Heterogeneous.
What does Twinkie mean?
Sorry, what was that?
I'm looking at what does Twinkie mean.
Oh, it's the cake that we're looking at. That's the picture.
Heterogeneous.
Very much so. Yeah, because you could take a bite out of it. You could have just cake in it. You could just stick your finger in and get cream out, or you could have cake and cream at the same time. So yeah, it's a heterogeneous mixture. So we're going to talk about physical changes and chemical changes. That's something that's going to be important for us to differentiate, to tell the difference between.
Excuse me.
Yes.
If we just have a cake without anything, is that heterogeneous?
Depends on the cake. Some people make a mixture of like vanilla and chocolate, and like they'll swirl it together.
I mean,
And so
without
you could tell.
anything on it. I mean, the cake has.
If you just make a plain cake, like a plain vanilla cake or something, then well, it would still be
New York style
heterogeneous because
cheesecake.
the middle would look different than the top or the bottom.
Okay.
So that would be heterogeneous because it would be brown on the top where it was baked, and then maybe like white in the middle. So that would be heterogeneous also.
Okay.
But if you just took out a slice in the middle, that would be homogeneous because any part you
But
took from that cake would be the same.
There will be many holes in the cake. Would that affect?
Then that's heterogeneous. Like Swiss cheese, there's like holes in it. That'd be heterogeneous.
Okay.
Air bubble.
Yeah, a bubble. If there's a bubble in there, well, just like the oil and water situation. If there's a bubble with gas inside of it, and we can separate that, then that's heterogeneous.
Mhm.
So let's look at this picture here. We've got sort of atomic scale views of something that's going on. So we've got A in the middle. So let me just draw on this thing. Get my marker working. Okay, got my marker working. So in the middle, we've got A. So focus on A, and then as it goes to the left to B, do we consider that a physical change or a chemical change?
Chemical change.
Which one?
Chemical change.
Chemical change.
Why do you say that?
Because they change the scale of their compounds.
Because I couldn't make out something about compounds.
The molecules decomposes and recomposes to different molecules.
Right, they're different. Yeah, they're different molecules. You can see with A, they're all the same. They're all two reds and then a blue. So they're all the same. But when we look at A, sometimes we have pure red. We have a red and a blue. So they're not all identical. They're not all chemically identical. So atoms have moved from one molecule to another. That is by definition chemical, because atoms have changed who they're bound to. That is, by definition, is a chemical change. Now let's look on the other side. Let's go to C. Now what happens between B in the middle and C on the right? Is that a chemical change or a physical change?
Physical change.
Physical change. They squeeze.
Yeah, they're squeezed together, but they're all the same molecule. So what we would say here is that A, most likely we would categorize that as a gas.
Mhm.
It's probably a gas because those molecules are far away from each other and they're not interacting with each other. Now, here with C, they're
Solid.
exactly the same molecules. They're just closer together. And so that is, yes, most likely a solid. I'd have to look at it over time to see if they could move at all. But yeah, I would say right there, they're so close together that's most likely a solid. So a transition from a gas to a solid is not a chemical reaction. That's a physical reaction only. So a physical reaction does not involve electrons being moved from one atom to another. The atoms and the molecules themselves are unchanged, but the way that they interact with each other is, and that's the big difference between physical and chemical. Okay.
Just
Yes. Go ahead.
what about uh, a light being like? What about electricity? Mm.
What about it? So you mean it's like if like
the
electrons going through a tungsten wire? Would we say that's physical or chemical?
Yeah.
Well, there's two. I mean, that is a physical change because there's nothing happens to the tungsten. It heats up, and energy is given to those tungsten atoms. And we'll learn later that those energy goes into the electrons in the tungsten atom, and they're excited into higher energy orbits. And when they fall back, they emit light. But the tungsten is not chemically changed in any way, so it doesn't undergo a chemical reaction. So that is physical.
But the battery does, right?
Battery is a chemical change. The battery itself is a chemical change. The electricity flowing through the wire is not.
Okay.
Yeah, because it's the wire would be the same before and after. The minute you and even during, I mean, the copper in a copper wire does not change into something else. It doesn't become oxidized. It doesn't change its charge.
Okay.
It remains constant. So that would be a physical. But yeah, really good question. Making me think. Damn it! It's so early in the morning. So characteristics that allow us, and this is one of the things we did in lab. We determined a property of a substance. We determined the property of one of the properties of ice that we looked at was its density, and we were able to identify it based on a physical property of that of ice. So a physical property is not associated with a change in its chemistry. So ice and water are exactly the same molecule, just in different orientations. The molecules are moving faster in one, the water, liquid, than in the other, solid. They're not moving as quickly. So the chemical composition doesn't change. And so these are some of the examples of things that we would consider a physical property, like its density, obviously. The color of something, whether it's hard or soft, like a diamond is hard and talcum powder is soft. That's a physical property of those particular compounds. Melting and boiling points are really, really important and that's something we would have done in lab. And I think we might do it in a lab this term, if I could find one. That is a way of determining whether or not you have a pure compound. How many people have seen, movies where, someone's buying a whole bunch of drugs and someone off on the side is like melting it, right? And they're looking at a thermometer, And everyone's staring at the thermometer, and when it gets to a certain point, then the guy goes, yeah, this is good. And then everyone, they make the drug deal and everything. What that guy is doing is actually melting cocaine or whatever it is he's got. And if it's a pure substance, it melts at a higher temperature. And so what they're looking for is, like, if the melting point is really, really high, that must be really, really pure. If it had a whole bunch of other, junk in it, it would melt at a lower temperature. And so that is something that you can do. And one of the labs that we normally do is that you would synthesize a compound and then determine its melting point to see how pure you're able to get it. Same thing that goes with boiling points. These are physical properties. And good thing I said electrical conductivity was a physical property. It turns out I might have been right about that, which is always good. So those are physical things. So physical changes are changes in what we call the state of matter. And the states of matter, if you remember from earlier, were solid, liquid, gas, and plasma. Those are like our four basic states of matter. So when wax melts, when a wax candle melts, there's three things going on. The wax is both solid, a liquid, and a gas in a burning candle. It's actually gas that is being burned off the wick of the candle. That's why, like, when you blow it out and then you put a match to it, it'll start burning without you actually even touching it. It's because some small amount of that paraffin wax is still in the gas phase because it's warm. It's still in the gas phase, and you can ignite it without even touching it. Now, steam is obviously a physical change as well. And so here we can see there's liquid in the pot, there's gas in between the lid and the pot, and then there's liquid on the bottom of the lid as well, because the lid is slightly cooler than the gas. And so when the gas hits the lid, which is a little bit lower in temperature, it recondenses back into a liquid.
Excuse me.
Yeah.
I was wondering when I was young, when I was lighting candles, what's the thread doing? I mean, we are lighting the thread. We are getting the fire of the gas of the candle.
Right.
What is that? Why is that happening? We are not.
Yeah, the first time you light a candle, it takes a while, right? I mean, you can't just like take a lighter, put it on a candle, and instantly it lights. It takes a couple seconds, and that's because there is paraffin wax on the wick, or the thread you were calling it. There's solid paraffin wax on the thread. And then you have to melt that into a liquid, and then that liquid turns into a gas. And it's the gas that's actually burning. And that's why the thread doesn't burn instantly, because you're not actually burning that very much.
Go
ahead.
So the paraffin. What's that?
Paraffin is the actual name of the hydrocarbon that candles are made out of. Most candles. It's like if it's a beeswax candle, it's something else, but usually it's a hydrocarbon called paraffin.
Okay. So the paraffin is on the thread, right?
Yep.
Oh,
yep.
Okay.
Yeah, so you've got solid paraffin on the thread, and then it becomes a liquid, and then at the tip it becomes a gas. And so it's the paraffin gas that's burning. And obviously the thread is going to burn a little bit, but not very much. And then as the candle burns down, the thread burns down with it, but it's constantly being fed by liquid paraffin on the thread being turned into gas.
Okay.
And so the solid melts, goes into the middle, goes on the thread, becomes a gas, and then burns at the top. So you're seeing like, yeah, 3 phases of the wax at the same time there.
Uh-huh.
So again, this goes back to the lab we did this week. The difference between, now some people say extensive and some people say extrinsic. You'll see both. Both words are used interchangeably. I'm generally going to say extensive and intensive, but sometimes I might slip up and say intrinsic and extrinsic because, you know, English people and American people say words differently. So occasionally I'll break down and not say them properly. But anyway, so an extensive property depends on how much stuff you have, like we were doing in the lab. Like mass and volume, if I've got a pound of gold and I've got 10 pounds of gold, it's still pure gold, but I've got 10 times as much over here. That's depends on the amount. That is obviously an extensive property. One thing we haven't talked about, but we will talk about later, is heat. Heat is something very important that's involved in chemistry. Heat and temperature are not the same thing. Heat is basically the amount of energy, the amount of thermal energy that an object contains. And then that heat will be transferred from something that's hot to something that's cold. And so the amount of heat, like say, for instance, the coffee, well, it's kind of cold now, but when my coffee was really, really hot and delicious, it had a certain amount of heat. But if my bathtub, if I filled my bathtub with water, but it was much cooler, the bathtub actually has more heat in it because the temperature and the heat is not the same. So we'll learn about that when we look at thermodynamics a little bit later.
Excuse me.
Yes.
But my high school chemistry teacher tells me that you cannot say something has a heat.
No, something has a temperature, but an object contains heat.
Okay.
Yes, you can definitely say that.
Oh, okay.
Yeah. So
Okay.
heat is just energy. So you can say something has energy in it. I mean, you have energy in you right now.
She
the
says
fact that your body is warm tells me it has thermal energy.
well, she says you can only say that object has inner energy, but you cannot say that object has heat. She said that.
Ooh, well, I hate to say she was wrong, but I guess I would have to say I would have to hear how she defined it, because you can definitely.
Well, I just translated it from Chinese to English.
Yeah, but you will see you can calculate very precisely how much heat an object has.
Okay.
Yeah, we have to be able to calculate heat in an object.
Okay.
Yeah, we can measure it quite precisely. What she might have meant is that we can only measure changes in heat.
Yeah.
Is that what you're talking about?
Yeah.
Yes. Then okay. I will buy that. But yes, because the absolute amount of heat is something that's very hard to define. Nicholas, question.
Yeah, I was wondering, is there something that has like the lowest specific heat where it just doesn't accept the transfer of energy, like certain metals or something?
No, I think everything, basically heat. Yeah, so a heat capacity is, and we'll learn this a little bit later as well. The heat capacity, or let me write it down. So, whoops, let me go back.
Vacuum.
Yeah, if there's nothing to, yeah, if it was an absolute vacuum where there's nothing, yeah, then I guess that would not be heated. But the heat capacity basically means how much heat does it take in joules, and we measure heat in joules. How much heat does it take to increase the temperature of whatever the substance is by 1 degree Celsius? So
In 1
everything can be heated. Everything. So it doesn't, it's like you say that some things can't be melted. Yeah, they can. So yeah, I have to agree. Yeah, the only thing would be an absolute vacuum because there's nothing there to absorb the heat. But yeah, every substance, every element, every compound, everything has a heat capacity.
So
Because when you heat it, it raises the temperature goes up.
So the only other thing in, I guess, technically in nature would be a black hole that doesn't have, like, that doesn't.
Yeah, but I mean, a black hole, there's heat in a black hole.
Oh, really? I didn't know that. Oh, okay.
Yeah. It's very, very hot in the middle because it's always pulling substances toward it and crushing them down to very, very small volume, and that releases a lot of heat. So they're very hot. That's how you can. That's how you can see them. You see on the event horizon, you see radiation of light and that's from things being heated and being sucked in. So yeah, so there's heat in a black hole. I mean, that's like physics stuff that I'm not. I'm no physicist.
Okay.
But yeah, I'm pretty sure it does. So, an intensive property does not depend on the amount of things. So here's where we see the difference between heat and temperature. So density doesn't depend on how much stuff you have. We learned that, right? We had a big piece of wood, small piece of wood, medium-sized piece of wood, all had the same density. And the temperature as well, because we'll learn that the temperature is based on the average kinetic energy of molecules. So if I have a cup of water and a gallon of water, and those molecules in each one are moving at the same speed, they're going to have the same temperature. So it's only dependent on the speed of the molecules and not the number. So the temperature is independent of the amount. Heat, on the other hand, is very much dependent on the amount, because it takes, to heat up a cup of water takes far less heat than to fill up a big pot. If you're making like pasta or something, it takes a lot of heat to raise the temperature of that. Whereas like 1 cup of water, you can raise the temperature of that much with much less heat. So heat is extensive, temperature is intensive. I know that's a lot of stuff we haven't got to yet, but it's good to start thinking about these things.
How about what's that? Electricity resistance.
Resistance. Yeah, resistance is based on the amount. Yep. So resistance in 2 ways. You can form resistance in 2 ways, right? You can change the resistor, which would be made of a different compound, or more and more coils of wire increases the resistance. So there's 2 ways. So resistance would be, that's tricky. That's a tricky one. If it's the same product, if it's the same substance, then would be an extensive property, because it depends on the amount. But if you're looking at the difference between like copper and aluminum, for instance, one would have aluminum has a higher resistance. That is an intensive property. So yeah, I don't know what you mean. That's a hard one, because that's both. Because you measure resistance in in the amount of like resistance per gram or resistance per meter or whatever it is. So yeah, that's a little bit of both on that one. So measurements. We talked a lot about measurements before and during the lab. And remember, this is something that I yell at students a lot, because A qualitative measurement doesn't involve numbers. So it's just like something you would see, like, like something changed color. And these are observations that, we say they're only qualitative, but they're really, really important. So that would be something you would put in your results as well. So if you were doing a reaction and all of a sudden, smoke sort of coming out of it, you might want to write that down. That tells you a chemical reaction is taking place. And so that's a qualitative measurement, but it's an important one because it says that there's a reaction. If it starts to get warmer, like if you don't have a thermometer, it gets warmer and you can feel it, that's a qualitative measurement. You don't know how much hotter it's getting, but you know it's getting hotter or colder. If something is precipitating out, that's a qualitative measure. You don't know how much is precipitating, but you can see something purple is forming and it's falling to the bottom. So those would just be words. I saw X happen. It was, blue, whatever. It was a vapor, or it was a solid, all these sorts of things. But anything that you have numbers on, that's automatically quantitative. I measured 1.20 grams of precipitate fall. So in that instance, you've got to have a unit. And I've mentioned over and over, and will continue to. If the answer to a question like, what was the mass of something? You can't say it was 12. That's not correct, because I don't know 12 what? 12 grams, 12 kilograms, 12 pounds, 12 ounces. I don't know. So any quantitative measurement has to have units in it, or it's not a measurement. It's just a number. And a number and a measurement are not the same thing. So every measurement has to give you 3 types of information. So the first one is just the magnitude or the size. That would be the number associated with it. So let's say I'm measuring something that's about a foot long. And so my first unit is 12.
Inches.
It's obviously going to be 12 inches, right? So the unit would be inches. So I put 12 inches. But the third thing that you need to include, and this is where sig figs comes into place, is
0.2.
how precise is that measurement? Now, if I'm just estimating, like let's say I'm just using my fingers as a measurement. Let's say I've measured how far my thumb and forefinger, let's say it's, I found it's around 7 inches or whatever, 6 inches, for instance, whatever it is. And so I measure something and I go 1, 2, so it's around 12. I put this down, and that says what would be my uncertainty here? How much uncertainty would I have if I just wrote the number 12? Like plus or minus what? So that would equal 12 plus or minus what unit?
2 inches.
Not 2.
Finger.
Generally means plus or minus 1. Generally so 12 plus or minus 1. If I just have 12 by itself, that means that it's not 11 and it's not 13. That's all it means.
Okay.
If I took out a ruler and it just had inches on it, so it just had 1, 2, 3, 4, 5, and so I measured with that, and those were the only units on it.
Subdivisions?
I could put 12, and I would estimate one more. So it would be 12. Let's say if it was right in the middle here, then I'd say 12.5. Because I have estimated the last digit. The same is true when I said 12. I estimated this. I know it's more than 10 because I know my finger's like 6, and it's like it took precisely 2 of lengths to measure something.
Excuse me.
Yep.
So if 2 is the estimation, would that be 10 plus or minus 4.
If I could only get to 10, if I just had 10, that is basically plus or minus 10.
I mean,
Because I basically, if I have 10 without any other information, that's just saying that it's not 0 and it's not 20. It's to the nearest 10. If I put another number, that means to the nearest 1.
okay.
Yeah. Okay.
Mhm.
If I have 10 with a period, with a decimal place, that means 10 to the nearest 1. But if I don't have the decimal there, it just means to the nearest 10. And 100 would be to the nearest 100.
Okay.
Okay? So there has to be some indication of how precise your measurement is. So if I give 12.5, basically I'm saying I'm estimating this last number. And so it's going to be plus or minus around 0.1, maybe with a little more uncertainty than that. But it gives you a sort of a general idea of, it's somewhere between 12 and 13, somewhere close to the middle. So it gives you more information than just saying 12, because I can actually see that it's more than 12. Now, if there were more subdivisions in between, I could measure the 12, I could measure the next digit, and then I would estimate the fourth. So then I would give a number like 12.55, because this I can see, this I can see, this I have to estimate. Now I have 4 significant digits. So it's all dependent on how many you can actually see with what you're measuring, and then how much you actually have to infer. Like you have to make an educated guess. If the measurement falls in between two given points, you have to estimate where it is in between those points. But it's really important that you do that, because it increases the accuracy of and the precision of your measurement. Okay. So that's why chemistry professors and physics professors are such sticklers for the sig figs thing, because if you're going to become an engineer or basically anything involving sciences, it's super important that you get that your numbers as precise as possible. like I said before, like when you're injecting patients with drugs, you better be really sure of like how precise that dose needs to be. Yes.
If someone says a person is 175 centimeters, how would you distinguish that if he or she is eyeballing or measuring?
Oh, because if you give a number of 175, that means basically what that means is it's not 174 and it's not 176.
I mean, how would you know that this is measured, not eyeballed?
Oh, I mean, if it was like halfway between, if
Like
it was halfway between 170 and 180, well, then in that instance, yeah, I mean, in that instance, you would have to give 175 plus or minus, and then a number. Yeah, or give it in. Yeah, no, yeah, you have to say plus or minus. Yeah, but this is like the difference if a scientist gives you a number or a layperson gives you a number. That's the difference. Okay. But yeah, that last one is always estimated. And so basically we would say that at least that means plus or minus 1. And so if the person did a decent job eyeballing it, that's probably close enough, right? Even if it was like off by plus or minus 2, that's still close enough.
Someone in the chat says that his last 2 physics professors didn't care about sig figs.
Good thing I'm sitting down. I would have passed out. No, significant digits are extremely important. I mean, yeah, especially in
Physics.
any
That's just-
science. Yeah, any science. Well, maybe not biology. I like to take a crap on biologists. They consider within a factor of 10 to be significant, but that's just based on what they're able to measure. But yeah, no, I would. These are really, really important because a lot of the people who are taking this class are going to be going into the health professions, and you're going to tell me that significant digits aren't important there. It's extremely important. So yeah, I reject that. Bad teachers.
Maybe they're just basic classes.
Yeah, even then, I mean, okay, I'll give you this. If it's not a lab class, maybe you don't get so
Because
worked up about
yes,
it. But if it's a
my
lab class, it's extremely important. And this
my
is a lab
actual
class.
teacher, not a professor, my actual teacher, when we do physics, he let us do how many digits you want, just that.
Yeah,
How many-
well, that ain't happening now, my friend. I have bad news. So let's go over the units. I mean, we sort of talked about this before, but we haven't really mentioned all the units. So, you know, there's 3 countries. I think it's only 3 countries that aren't using the metric system now.
US,
Anyone know what they are?
US, UK,
No, UK uses it.
okay, USA, and
Liberia, Myanmar, and the United States. So that's like some excellent company to be keeping. The rest of the world has been using the metric system for a while. I'm from Canada. We started using the metric system when I was in middle school. So it was
could you
in
say
the
the
70s?
country names again?
Liberia, Myanmar, and the U.S.
Only US is a great country.
So those 3. Yeah, and it used to be South Africa as well, but now South Africa's like jumped on the train as well. So but in science, they've been using the metric system for a lot longer than that. Basically, scientists have been using the metric system for like the last 100 years or so.
Does UK not use imperial system?
No, I think if you buy gasoline or petrol, if you buy petrol in the UK, you buy it in liters now.
Okay.
Yeah. So these are sort of the base units we're dealing with. So length, we're probably familiar with the meter. A meter is around 3 feet long, a little bit longer. It's about 39 inches or so. The kilogram is the standard unit of mass. And the kilogram is, the kilogram is actually the mass of 1 liter of water. That was like the original way that all these units were sort of tied together was through water, and that made a lot of sense. So 1 gram is also equal to 1 cubic centimeter of water. Time is still seconds. All right, that's cool. Temperature. Now in science, we use Kelvin. Anyone remember what Kelvin is? What's the difference between Kelvin and Celsius?
Negative 273.15 degree Celsius.
Is absolute 0, right?
Mm.
So basically, Kelvin, there's no negative numbers. It starts at 0 and just goes up. And we only really use Kelvin when we're completely when we're talking about gases. Pretty much everything else we can get away with using Celsius. The reason is the units of Celsius and Kelvin are exactly the same. So 1 Kelvin, the difference between 1 Kelvin and 2 Kelvin is exactly the same distance between negative 271 and negative 270 Celsius. So each degree is exactly the same distance away. So when we're talking about changes in temperature, we can use Kelvin and Celsius interchangeably.
Mhm.
We use Kelvin when we're talking about gases because when we deal with the gas laws later on,
Directly proportional to
yes,
some.
Kelvin is directly related to the amount of thermal and physical and kinetic energy that molecules have. And it only stops when you get to 0. And so everything above that is positive. And so that's true with gases. So we use Kelvin measurements for that, but we use Celsius for pretty much everything else. Now, the amount of substance, we're going to be talking a lot about that, is the mole. 1 unit of a reactive thing, an element, a compound, whatever it is, 1 unit of something that reacts is a mole. And we sort of talked a little bit about that already. But that is and what is the measure of a mole? It's whatever the atomic mass is in grams. So 1 mole of oxygen is 15.999 grams, because that's how much a mole of oxygen weighs. That's how much 1 atom is 15.999 atomic mass units. But we can't measure atomic mass units. Like, I can't measure atomic mass units. Grams I can measure all day. So that's why we use the mole. Okay. Clear all these out.
Candela.
Yes.
I'm just saying candela.
Oh, yeah. That's the amount. Yeah, that's how you measure the intensity of light, is in candles. So that makes sense. So the other part of the metric system that makes it much easier to use than the imperial or the American systems, that everything's in base 10. And so the calculations are you can do them in your head. Whereas trying to figure out the number of feet in a mile in your head is pretty much impossible. There's 2.5 miles. How many feet is it? I don't know. You got to get a calculator and you got to work it out. But how many meters are there in a kilometer? 1,000 instantly, because it's all 10. So the difference between units are given in these prefixes. And so these are the most common ones that we use are in bold. So when you get to really, really, really small numbers, down here, like in the lab, like in a biochemistry lab, for instance, when I would be ordering reagents, I'm ordering them in femtogram amounts. And it's really important that you get those measurements properly, because you'll end up spending like tens of thousands of dollars that you didn't want to spend if you mix up femto and milli. So that's a huge difference in the amount. So as far as big amounts, we're really only going to use kilo, like kilogram, kilometer. That's really that's the only bigger one we're going to use. Although occasionally we might use mega. Everyone likes to think things are megabytes, gigabytes, terabytes. Those are all factors of 10, lots and lots of factors of 10. And you can see that when you get to like really big numbers and really small numbers, they change in factors of 1,000.
Excuse me.
Yeah.
So someone says kilobytes, 1,004 bytes. Someone says it's
1,024 actually.
Oh, okay.
Yeah. It's because those are all in base 2.
Okay.
And so there's no such thing as you can't get 1,000 bytes, because you can only get them in terms of 2. So the closest thing you can get to 1,000 is 1,024, I think. And so, yeah, it's not exact with bytes, because you've got a binary system.
Okay.
So I think someone who knows more about like a computer scientist hopefully will help us out. But yeah, I think a kilobyte is 1,024 bytes. It's the difference between bits and bytes as well. Yeah. Anyway, we're dealing with chemistry here. So So for far as things are bigger, we'll generally only deal with kilo and mega mostly. But in terms of smaller things, we deal with that all the time because we're measuring really small amounts of stuff. So centi means 1/100th. So centimeter, everyone's probably familiar with a centimeter. That's 1/100th of a meter. And then, so millimeter, that's 1/1000th.
Micrometer.
And then when we get down, then once we get even smaller, then again, we start jumping in
Nanometer.
10 to the -3, or we start dividing things by 1,000. So we can get down to really, really small numbers. So micro is 10 to the -6 or 1/millionth. Nano, 10 to the -9 or 1/billionth. Pico, and that's like, when you start dealing with pico, you're dealing with really small amounts. That's 1/trillionth or 10 to the -12. Femto, -15, so that's quadrillionth. And then there's two more, and these are my favorite. So atto is 10 to the -18. And then zepto, which is zepto, is 10 to the -21. And when you're getting down to numbers that small, you remember, if you remember from high school chemistry, that 1 mole of something is 6.022 times 10 to the 23rd atoms or molecules. Once you're getting down to zepto, at 10 to the -21, you're dealing with basically hundreds of atoms. So that's a number so small that it's practically impossible to measure. That, I mean, there's certain things you could measure with you know, that kind of small, but the measurement would not be terribly accurate if you're measuring zeptomoles of something. That's really, 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 really small. But the ones you should remember, focus on, are kilo, centi, milli, and micro. Those are the ones that we're going to be doing over and over and over and over again. So if your brain could only handle so many, those would be the 4 I would try and remember. So yeah, this just explains when we're moving our decimal one way, if we're moving our decimal another way. Just remember, every time you move a decimal, you're changing by 10. So if you're moving from meters to centimeters, you're moving to the right, you're increasing the number. And so if we move it 2 places, we've moved it 100, and so we've multiplied by 100. Going the other way, every time we move to the left, we're dividing by 100. So remember that every time you move one to the right, you're multiplying the number, you're making a larger number and a smaller unit. And when you're going to the left, you're making a smaller number and a larger unit. So let's just do a quick one here. We're running out of time. Let's just do a quick one here. So 612 grams. How many milligrams is that?
6,120. Oh, sorry. 6,120,000.
So 612,000?
Yeah.
Yeah, so it'll be 1,000 times. So a milligram is 1,000 times smaller than a gram. And so we'd have 1,000 times more milligrams than grams. Now, what about meters? How many centimeters would that be? 8.160 meters.
816.
Nope.
0.
0.0, yes. That number, that 0 is there for a reason. That number is there for a reason because it tells us we've measured that number to that precision. And so we can't just throw precision away. So we need to, that's why this number is there for a purpose. If, on the other hand, it was 860, this is just a placeholder. This just tells us how big the number is. It doesn't tell us how accurately that number was measured. Now here's a trickier one, 3,779 micrograms. What do we do to micrograms to get to grams?
0.3 zeros. 2 zeros actually.
Yeah, so the difference is a million. And how many zeros are there in a million? There's 6, right? So we would have to go 1, 2, 3, 4, 5, 6. Yep, so you're off by 1. So it's 0.003779 grams. Yep. So these are the, we have to go back and forth. Now, this is something we're not going to have to do very often, because basically I'm not going to be giving you measurements in English or American measurement. I'm not going to give you like a gallon of water, but sometime you will come across these, because I mean, it happens in real life. You're going to have to make that change. So all of these, why this particular measurement is highlighted, because that is the only one that's exact. 1 inch is exactly 2.54 centimeters. So everything else, when I'm measuring 1 kilometer, I can make that as precise or imprecise as I want. I can have 0.6214, and I can just keep going with numbers. But in this instance, 1 inch is equal to 2.540000.
Is that defined
Indefinitely.
that way?
That is defined. Yes, that is a definition.
Okay.
These are estimates.
Okay.
These are all estimates. This is a definition. Yeah. So however many significant digits you have in your inches, you can have that same number of significant digits in centimeters. Yeah, because it's precise. It's absolute. So if I give you any of these like on a test or something, in a quiz or whatever, you can just look. You can just look. You don't have to remember any of these. I'm just basically the takeaway is. I want you to know that this is unique. That basically you can define 1 inch as 2.54 centimeters. It's not a. It's one of those weird things that just happens to work out exactly. Weird. But,
Do you
know,
have a schedule of our testing quizzes
Not yet.
on Canvas? Okay.
Not yet. I usually give one at the end of chapter 3. So I'm probably in about 2 weeks,
Okay.
3 weeks, thereabouts. We have our first one. But yeah, we haven't done enough stuff yet. So again, relative lengths and absolute lengths. So a meter is a little more than a yard, about 3 inches more. Centimeters, obviously 1/100th of a meter, but an inch is exactly 2.54 centimeters. So we have done this already. So I'm not going to spend a whole lot of time in this because we're doing this, and we'll continue. You'll continue to do this for the rest of the class. It's just changing one quantity to another quantity, and we're going to have to do that. We're going to have to do this all the time because you're going to be measuring things like temperature and converting them to things like heat. You're going to be measuring grams and converting them to moles. You're going to be doing this all the time. And so it's something that we need to get really comfortable with. And so, and it's based on this one overarching principle, is that whatever the quantities are, you have to multiply or divide them by the same mathematical operations as the numbers. So if I'm changing inches to centimeters, what I'm basically doing is multiplying this by 2.54. So I'm changing the unit, and that means I have to change the number associated by that unit by the same thing. And every time I multiply, and remember, I don't ever want to see you dividing. things, never divide things. The reason is I want you to multiply something. So if I have 1 inch and you want to convert that to centimeters, what I want you to do is have centimeters on the top and inches on the bottom, so that when you do your change, you put your 2.54 up there. When you do your change, you can cross out the unit you're not interested in, and the unit you're left with should be the answer you're looking for. And the reason why I want you to do it that way is sometimes you're going to have to change 3 or 4 units at the same time, particularly when we get to gas laws. When we get to the gas laws, we're going to be measuring pressure, volume, temperature, and the number of moles. And there's basically there's a unit that puts all 4 of those together. So we're going to have a lot of different units at the same time. And if you don't have them lined up exactly right, you can get radically wrong answers. So it's really important to, don't just divide 2 numbers and go on. Make sure you multiply with the units there. And I'm going to make this point about 1 trillion times until you get tired of hearing it. But it'll prevent a lot of issues down the road. I mean, I still do it, and I'm old and stupid, so I have to. But you're young and smart. You should get into this habit before you get old and stupid like me.
Fine.
So here's your so these are the conversions I was telling you about. These are your equivalent. So it depends on whether you're converting centimeters to inches or inches to centimeters. The other point I wanted to make is that any conversion, any dimensional analysis, any conversion you do, one way to think about it is that the top and the bottom of these must be equal to 1, right? So 2.54 centimeters has to equal 1 inch. Why? Because I'm multiplying by 1 here. I'm multiplying by 1. Because when I'm changing the unit, that's all I want to do. I just want to change the unit. I don't want to change anything else. And so when I have a number, let's say I have, 2.76 feet, and I want to change that to centimeters. So I have to do 2 conversions there. But I don't want to change the amount of feet. So whatever I multiply that by has to be 1, because 2.76 feet at the end has to equal so many centimeters. So I can't multiply it by 10 or multiply it by 1,000 or multiply it by 1,000,000. I have to multiply it by 1 so that my 2.76 feet at the end equals that precise number of centimeters. So every time I multiply it, when I'm changing my units, whatever I'm multiplying by must equal 1. So that's important to remember, and that will help you remember what conversion to make. So 2.54 centimeters equals an inch. 12 inches equals a foot. So when I multiply something by this, I'm not changing it in any way. I'm just changing the units. Any questions about that? Like, does it make sense when I say when you multiply by 1, it just means whatever's on the numerator must equal what's on the denominator. There might be different units, there's going to be different units, but they must equal exactly the same thing. Or else you can't, you're multiplying by something other than 1, and you're going to screw up your results. Okay? All right, let me just power through a couple more and then we'll finish up. So I really want to get to chapter 2 as soon as I can. So these are some of the common conversion factors. You can make a copy of this slide. Remember, all these slides are in PDF form in Canvas. So if you want to print any of them out and just have them with you, please do. It might be faster than having to look them up every time. So this just goes on just what I've been nattering about. Always have the units when you're doing the conversions, because the units will set you free. The units will be a guide as to whether or not you're doing the conversions properly. Because once you cross everything out and you're left with the unit you're supposed to have, then you've probably done it correctly. At that point, the only 2 things you could screw up is getting the wrong number of centimeters in an inch, getting the wrong number of inches in a foot, getting the wrong number of pounds in a kilogram, whatever it is. Or you have like big stupid fingers like me and you mushed like the wrong button on your calculator. But if you set up this properly, you're going to get like 80% of the points. So even if you made mistakes, if you set it up properly and then, mushed three buttons at the same time, no worries. You're still going to get 80%, maybe a little bit more if I'm feeling in a good mood. So that's why you should always show your work. Because if you just give me a number, I don't know how you did that. I don't know if you just like looked it up or whether you asked a friend or, whatever. But if you showed me the work, how you got to it, you're going to get the full marks.
What if someone gets the process wrong and like accidentally get the results right? And
They're going to lose some points
okay.
because they did it wrong. Yeah, you stumble into the truth, then sure, but that's not good enough. So what I'm gonna, go ahead.
Nothing.
Okay, so I'm going to leave this problem for you guys to do, and then we will pick it up on Tuesday with the answer, and then and how we did it. So we're just going to leave it right here. Okay. So any questions before we shut down for the morning?